Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math basic course, and as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Step one aside as we begin the Integrated Math 3 textbook from Big Ideas Math. We start with Chapter 1, Geometric Modeling. Section 1.1 is on modeling with area. And then we go to modeling with volume and then some other things. I think cross sections of solids and solids of revolution, something like that. Only 4 sections deep, which is pretty nice. And if you follow along with this entire series, what we're going to do is updating on a day-by-day basis. If you check out the description section down below, you're going to find an IM3 playlist where you'll find every single section within this stuff where I do solution guide videos and lectures for them. As I'm going to begin this one in section 1.1 on modeling with area, I'll begin with the lecture portion out of the textbook. You can download that PDF down below and check out the timestamp when I go to the problem set where I do the solution guide video, the solution guide portion, I should say, and it's numbers 1 through 20 as a whole. You'll see that there's a vocabulary and core concept check with the first 1 or 2 questions, or 2 or 4 questions in general, and then after that you do the whole problem set as well. So follow along, take a look at this stuff, ask questions in the comments if you have any. I'm going to go ahead and get started with this lecture portion here. Now, as we begin IM3, this stuff starts off with geometry, and then it kind of leans into more algebra stuff afterwards. So I wouldn't call it a precursor. It counts as IM3, but it uses a lot of previous materials that you would have known before just to include a brand new item here in population density. And full disclosure here, by the way, guys, I sight read this stuff. What that means is that I haven't really looked at this before. All I did was formatted it so that it fits onto the screen the right way. But outside of that, I haven't done the problems yet, which is kind of nice in some ways for people to see how I walk through and talk through a problem by seeing it for the first time. So I always apologize if there are mistakes that I make or if I stumble along the way or something like that. Generally, I'm pretty good. But it's a nice improvisational way to do things, plus it saves me a lot of time for not having to do something twice. So I only trust that I do things the right way the first time, and, judge for yourself whether it's right to you, if that makes sense. Just a little heads up. Okay, so perimeter area and surface area are going to be used from previous items, whether it was IM2 or something else from before, and I'm sure that we can recap what this stuff means. But otherwise, I'm going to kind of assume you know what most of that means. To learn population density. Now we're going to learn how to use area formulas to solve problems and use surface area formulas to solve problems. In this case, it sounds like, and it looks like here they're referring to word problems or things with bases regarding context. All right, population density of a city, country, or state is the measure of how many people live within a given area. So it's number of people divided by area of land. So if a population is more dense, that means there are more people per square mile, per square, whatever it is, right? They pack themselves in more. It's usually given in terms of square miles, but can be expressed using other units such as city blocks. Okay, so assuming the city blocks are a regular, 400 people per city block, something like that. Assuming it's kind of a uniform value, I think that makes sense. Probably square kilometers in other areas of the world, though, right? All right, finding a population density. Example 1. Let's take a look. The state of Nevada has a population of about 2.7 million people. Find the population density in people per square mile. So you can see that they're showing you some version of Nevada with these values here. It looks like we're going to have to find the area ourselves in order to use that formula. So step 1, find the area of Nevada. It's approximately shaped like a trapezoid. So it seems like we're going to have to base things on not only our understanding of certain shapes and approximate it. And I agree. Look, there's a part that's chunked out, but we're not going to really deal in terms of that. We're just going to work it the way that we see it. And we have to know its formula. Area of a trapezoid, you average your bases and multiply by height. That's the way I say it. They do 1/2 height times base 1 plus base 2. Your bases are these two guys right here that are parallel to each other. And this is your height here. So height and base 1, base 2, whatever, something like that, right? So they approximate the area to 110,400 square miles. And then we will divide the population of 2.7 million people, which is 2,700,000 people, divided by that. And they say around 24. That's 24 people per square mile. I don't have the exact calculation there. I'll be doing calculations on my own. But that's what they're saying here, which is, it seems sparse, but you have to think about the fact that there's a lot of places all around where there are no people. And that's true in California and everything else as well, but just that, that's just the average population density. I'm sure if you narrow it to other areas, like a certain city or something like that, you'd get a much larger value. Whereas some other places you get 0, right? 0 people per square mile in the desert areas. All right, using the formula for population density, I guess once again, a circular region has a population of about 430,000 people and a population density of about 5,475 people per square mile. Find the radius of the region. Now this time we're missing area stuff. We know it's circular, so our area is pi r squared. We're basically going to solve for r in this scenario, understanding that the area of the land is the part that is unknown to us. This time we know the density, and we know, once again, the population here. So do what you need to do to get r by itself in this scenario. They're going to first multiply both sides by pi r squared. Times pi r squared, it cancels here, and times pi r squared, it doesn't cancel there, it's present. And then you divide both sides by 5,475 pi, and take the square root of both sides. And they're showing all the work appropriately there. That you take the square root of both sides, you get a radius of about 5, apparently. We're going to have to see a problem just like that when they give it. So this drawing doesn't represent the circular region, but understanding it is a circular region, that's what we're going to have to do for that r. So with the region being about 5 miles, that's what's going to give you that density based off that population. So pi r squared is the area of a circle, and something that sounds like we're going to have to know. All right, third example using an area formula. You're designing a rectangular corral. A barn will form one side of the corral. The corral is to have an area of 450 square meters. But you want to minimize the amount of fencing you need for the 3 sides of the corral, not against the barn. This will include an opening that is 3 meters wide where a gate will be placed. It's a lot of information, even for me. I'm taking it in. Thankfully, they're doing the example for us so we can picture it together. How many meters of fencing do you need to build the corral? All right. It always helps to have some sort of drawing. They didn't seem to... Okay, they do have a drawing later, so we'll look at that eventually. But, you know, once again, they have a barn on one side, so that's not a part of your fencing, right? If this is your barn here, the other 3 sides are the fencing themselves. So here's fencing, fencing, fencing. And they say, how many meters do you need to build the corral based off stuff? An opening that's 3 meters wide, blah, blah, blah. We'll see what they want to do with that eventually. Let's follow what they say. That's why we're here. Use what you know about the area and perimeter of the corral to find an expression that represents the perimeter of the 3 sides that need fencing. The area of a corral's length times width. So 450, they say that's your area. 450 square meters is length times width. Okay. And then they say solving for L gives you this. Now, the reason why they have you solve for L is to use L to be represented in your perimeter formula in a different way. Use it in terms of W. So take a look at this. To minimize the amount of fencing, you let a longer side of the corral be against the barn. So whenever they say length and width, and I mentioned this in other videos if you've seen them from me before, that I learned kind of later in life that length is always longer than width. So they're referring to getting length by itself because they want the barn to be on one of the longer sides, so they minimize the amount of fencing. If this is our barn, then these are our widths shorter than that other length. So the perimeter of the fencing is going to be this width plus that length, or 2W plus L. Not 2L, because the barn doesn't have any fencing on it. So that's just the representation. That's where the drawing kind of works. I don't know where the 3 feet of fencing works just yet. But there's that. But L is also 450 over W. So you can re-express perimeter in terms of just W by substituting 450 over W and for L. So now we have an expression for the perimeter using only width, one variable, which is nice to have. And in doing so, we're going to do some tests. So they say use the table feature of a graphing calculator to create a table of values to find the width. And I do have a graphing calculator here. I don't know if you do as well. I assume if you're an IM3, that's probably something that you start to use eventually instead of a scientific one. However, some scientific calculators can also do equations. But you create an equation here. You use X instead of W. That's just something by nature you're going to have to do. And then Y is basically your perimeter. And if you work some things enough, it looks like when they find certain increments of 4, they're going to land on a certain width that minimizes your perimeter. Excuse me. Minimizes the perimeter. The least amount of fencing you'll use and still maintain 450 square meters. 450 square meters of this. So apparently, with the width of 16 meters, that's exactly what that thing does. Oh, no, it looks like it can shrink even more. So it goes to 15 eventually where they see the minimized amount. So 15 meters is that, therefore the length will be 30 meters. You do 450 divided by 15 to figure that out because that's the length expression. So we get 30 meters of that. They do say sketch a diagram, and this is where apparently the 3 meters of fencing comes in. Not a part of your official calculations, but just, we have how much fencing you need eventually. If the entire length of the thing is 30 meters, but there's 3 meters of fencing cut out of it, that means there's only 27 actual meters of fencing, whereas the other 3 meters finish off that length. So it's the same idea of what we said before. This is 15 and this is 15. That whole thing is 30 as in its entirety. But we cut out 3 feet for fencing. All right, so that was a lot in that problem there. Even, it took on a lot for me to kind of explain it, and I hope that made some bit of sense. We still have at least one more to do here. It's probably the last page of notes before we move on to the problem set. Let's take a look at this one using surface area. Now, I don't know what surface area formulas you'll know, so I'll have to just state some out loud from what we have, or they'll give them to us. I don't know. A manufacturer designs the bearing shown. To prevent corrosion, the manufacturer coats each bearing with an anti-corrosive grease. Okay. A smaller bearing has linear dimensions that are half the dimensions of the bearing shown. So whatever's shown right here, 20 meters, take half of it as 10, 2.5 millimeter radius, half of that would be 1.25, 1.25. Does a smaller bearing require half the amount of grease that's used to coat the large bearing? Explain. It's a good question. The answer is actually no, but we'll get to that. And then a smaller bearing has the same radius and height that is has the same radius, and it has a height that's half the height of the bearing shown, is half the amount of anti-corrosive grease used to coat that bearing. I believe that one's yes. Okay. Let's answer this one at a time. So the first one says, let's shrink both of these sets of dimensions by 2, both the radius and the height. Make this 1.25, make this 10. Now let's actually compute the surface areas of both sets. Let's find the surface area of this cylindrical, what do they call it, bearing? This cylindrical bearing by using this formula here, 2 pi r squared plus 2 pi rh. I actually write it the other way generally, but this is the lateral area, the area around the cylinder, and this is the area of both of your bases on top and bottom. You add those together, the lateral area plus area of both bases. Now, if we do the original cylinder here, you're going to get around 11.25 pi, well, exactly, 11.25 pi square millimeters as that one. Let's compare it to the other one that we're going to have to do where we divide this by 2 and divide this by 2. They're each half of what they were. And you can see this calculates to 28.125 pi square millimeters. When you divide one by the other, it doesn't become half the surface area, it becomes a quarter of the surface area. And there's reason for that. If they're not going to go ahead and explain it very much, I think it's just us exploring that idea. But areas are the square of the scale factor of their original values, not equal to them. So yeah, it's 1/4 the amount of grease that's used instead of half of it, even though we reduced everything by 1/2. Now, part B is where we do keep the radius at 2.5, but they do shrink the height to 10. So when you calculate this new guy right here, you get 62.5 pi square millimeters for the surface area, where just the height is shrunk, but not the radius. And you compare those ones, and it's not half. It ends up being 5/9 times the surface area of the larger bearing. Interesting. I thought it was going to be half. Because 5/9 is greater than 1/2, half of the amount is used to coat the larger bearing. Oh, it's not enough to coat the smaller bearing. 5/9 times it. Because it's more than half of what it is. It's more than half of what it is. Yeah, so that's gonna work. Okay, I skip all the monitoring progress questions because I feel like it's more things that we're gonna dive into more, and I'll just let the ones that are typed out be there. Okay, pretty long lecture in general. I don't always anticipate how they're gonna work out because, like I said, I don't look at them beforehand. But let's jump to the vocabulary and core concept check. After that, we'll do the numbers 3 through 20 for the main problem set. Okay, explain in your own words the difference between the population of a state and the population density of a state. So, the population of a state is the number of people, period, regardless of area. The population density, don't worry, I'll shrink this right now. The population density is the amount of people, is the number of people per area of land. So, one is a rate, right? One is a quantity quantity, the first one, 1 is a rate. And, that rate, you can have a population density of 100 people per whatever square mile. And that could be relatively small or relatively big. I guess it's relatively small. I don't know. Anyway, but the population itself can be massive or small in comparison, but it's not comparing to land, right? You can have 2 different states with a population of 1 million, for example. And if one state is massive in comparison and it has a more sparse density, the density is going to be smaller. It's going to have less people per thing. Anyway, let's keep moving on. Number 2. Which one doesn't belong? Which expression does not belong with the other 3? Explain your reasoning. There are bears per square mile, video gamers per city, people per square kilometer, or trees per acre. What I would generally try and do here is I'll mark one of these as A, for example, and if others are the same as it, as far as what they're comparing, I'll mark the others as A and the other one as B. Bears is not people, video gamers and people are people, trees are not people, so it's not about that. Per square mile, per city, square kilometer, and per acre. City is not a uniform kind of area measurement, right? Square mile is, square kilometer is, and even acre is. I don't really know how acres measure, but I'm not really good at that. But I'd say these are all the same as far as they are comparing to actual areas. Per city may be some form of density, but city is not a uniform area amount in comparison, not area measure. It has the right idea. It has the right idea of density, but it's not quite the same. Okay. Anyway, guys, I'm going to jump into now the numbers 3 through 20 portion of this thing right here. So again, this is the problem set, the main problem set. So if you'd like to jump along with me, we're going to go ahead and get started with this one together. Okay. Now, you might have to have your calculators out as well. There's a lot of division that has to be had, so get ready for anything. Numbers 3 through 8 find the indicated measure. The state of Kansas has a population of about 2.85 million people, and let me just write that. So, POP equals, and let's write it the actual way, 2850000. Okay, find the population density in people per square mile. Now, what they show you for Kansas here is it's basically a rectangle as far as area goes. So area of Kansas, we're going to do length times width, which is 400 times 210, which is 8, 4, and how many zeros? That's the only problem. I'm going to get this one wrong. 0, 0, 0, 0. Probably one more 0 there. I'll actually use the calculator. It's probably something that's relatively simple, but I don't want to mess up in the very first problem that I do. Nope, 1 less 0. So, okay, 84,000 square miles. All right. So when it comes to actually doing the density, I'll just write it as D. D equals, we take the population and divide it by Z density. And I'm going to go ahead and use the calculator again for that. And they seem to be doing a lot of rounding without decimals. So I'm going to make sure to do the same, especially when it comes to people. We're probably not going to say something like, oh, about 7.5 people. We'll just say, so this is 33.9-ish, 33.928. So I'm going to say about 34. So about 34 people per square mile. That is going to be our population density of Kansas. And I assume this is accurate to whenever this book was made, as far as what they said for the population and that thing. They try and stay pretty accurate with that stuff, it's kind of fun to see. All right, number 4. About 210,000 people live in a circular region with a 12-mile radius. Find the population density in people per square mile. So once again, we'll have population, I'll just call that P. Population 210,000 people. Area is of a circular region, pi r squared. So we're going to be doing pi times 12 squared, which is 144 pi. Do your best not to do any rounding early. Leave it in terms of pi for now and let the calculation work itself out as needed. So now density this time we'll have this is, by the way, square what? Square miles. And this is people. 210,000 divided by 144 pi. Now, if you use the calculator, I did say leave things in terms of pi for now, but I will be dividing out pi. If you use your calculator, I'm going to pull up mine. I'm going to do 210,000 and divide by 144 pi, but don't do this. Don't do this right here. This answer is going to be wrong. Wrong. What happened to this is this took 210,000 divided by 144 and then multiplied that result by pi. If you want to get this proper, you need pi in parentheses with the 144 like that. This will be the correct answer here. So this density, we're going to say about 464. 464 people per square mile. All right, here we go. 464 people per square mile. In that circular region. I don't know how often we talk about circular regions of cities and stuff. Normally they're district drawing kinds of things are a little bit less circular. All right, number 5. About 650,000 people live in a circular region with a 6-mile radius. Find the population density. So we just did one like it. Let's jump into one again. Not much to explain this time. I think it's the same old as you just saw. So that many people, and then area is pi times 6 squared, which is 36 pi square miles. So once again, doing the same thing unless I missed something. Circular region, nope, same thing. So 650 thou divided by 36 pi. This time I won't show you the calculator. I'll just go ahead and calculate it. 650,000 divided by... And I hope I type all my numbers of zeros correctly on these things. If I make a mistake, do correct me in the comment section. This is significantly bigger, 5747 people per square mile. Now, when I say bigger, well, there are more people, but it's not always necessarily more people. See, this is a smaller population and larger area. This is a larger population and smaller area. What you're going to see here, and I should have said that beforehand, is this would be significantly denser. Significantly denser. There are a lot more people per square mile in this area, circular region, than this one. And they don't ask us to compare those two, but that's what I'm doing for you. Number 6, we have a table. Yellowstone National Park has an area of about 2.2 million acres. Now that's, the area is already calculated. There's no other thing to state outside of that. The acres are the area. The table shows the estimated park populations for several animals. Find the population density in animals per acre for each animal. So when we do this division of let's see. So we'll say area equals 2.2 million. So 220 acres. So we have a couple different things here. For grizzly bear, I'll just say bear. For bear, the density is going to equal 445 bears per this amount. I'll just kind of get these set to start with. Elk is going to be this number divided by that. And then we keep moving. Mule deer. Let's put deer. Or mule. I don't know which one it really is more so. I've never heard of it. Is that made up? Are these numbers accurate? That should have 2 sets of 2s there. That's the right thing, right? 2, 2, 2, 0, 0, 0, 0. And the last one, we have bighorn sheep. I assume it's deer if this is, I assume this is not a bighorn. 2, 2, 2, 0, 0, 0, 0. Okay, I have a few things to calculate. Find population densities for each of these. Now, they are all compared to the same area thing. So whatever's the smallest amount, the sheep, is also going to have the sparsest density. It's going to be the least of them. So it just kind of moves like that. So 445 divided by 222, 0, 0, 0, 0. Okay, so first one. Now, this is interesting. Let me show you this on the calculator. For the bear, they have this number. This isn't 2. Notice it has this number here. So 2. So this works like this. I'm going to go back here for a second. This is scientific notation version of what that is. Now, what this means here is this is 2.0, and then we move this decimal 1, 2, 3, 4 places over like that. So there are 3 zeros that front this thing here. So what we're looking at, this is one where I don't do much rounding. I mean, I'm going to use the 2, but it does say per square, per acre. So this is going to be 0.0002 bears per acre on average, right? That's its density. That's how that thing works out. And so, I mean, it's rounded still, right? It's a rounded value, but that's the idea that you're going to have to do for that thing. It's a small amount. There aren't many grizzly bears per acre, right? So that's the idea. Anyway, we're going to do the same thing for all these other ones. They will all feature decimals, but that one specifically use scientific notation when the calculator has something too small to work off of. So let me do some others with you here and take a look at what they are. 20,000 divided by, I believe that number. So let's round that to around 0.009. And I'll give the approximation equal signs, 0.009. You don't have to look at what I'm writing, but elks per acre. Yeah, I want to make sure that's the pluralized version. Deer, 2,400. And then this is around 0.00. I'll put 1,1. I feel like that other one kind of rounds up to that. Deer, not deers, per acre. And by the way, units matter on these things. And the last one, this will probably give us that same scientific notation as we just saw from the other one. And yeah, so this is going to be 0.0001. I don't know if I should include the 2 after 0.0001 sheep per acre. All right, so these are my final numbers here that I had written down. So hopefully it's kind of making sense where those come from. But again, the units matter to write. If you hadn't been doing it before, please make sure you're kind of going back to do that and you're adding them now. Especially when we're talking about these being rates versus what was before population. All right, number 6 basically had 4 parts to them with that same acreage amount. Let's go to number 7. A circular region with a 4-mile radius has a population density of 66 people per square mile. Find the number of people. So we're going to use the same formula, but this time we don't know the population. We know the density, and we know we can figure out the area. So the area is going to be pi r squared, 4-mile radius, means 16 pi square miles. And the density, which we do know, 66 people per square mile. That looks weird to abbreviate like that. I might have to write the word people out. So 6366 equals this unknown population divided by 16 pi. So we got to figure out p. We're going to multiply both sides by 16 pi to figure that out. And it's that simple. There's not much more to it. We're going to let your calculator do the rest, do some rounding, and make sure we call it people as our final result. So 16 pi times 6366. And I'll let my calculator take care of that. We're getting around 319,990 people. That's the population itself. To have that density, and that makes sense. That many people per square mile times the number of miles. Square miles, right? That's what we get out of that one. Okay, number 8. Central Park in New York City is rectangular. Yeah, it is. With a length of 2.5 miles and a width of 0.5 miles. During an afternoon, its population density is about 15 people per acre. I don't know how much an acre is, though. I'll have to look it up. Oh, here it is. Find the number of people in the park that afternoon. 1 acre is equal to 1/640th square miles. Okay, so for number 8, let's do this to start with. The area of Central Park in terms of square mileage is 2.5 times 0.5. Whoa. Which is half of 2.5. I don't need a calculator for that. It's 1.25. 1.25 square miles. For some reason, I thought it was bigger. I mean, that's big, but for some reason, I thought it was bigger. So if 1 acre is 1/640th square miles, right? 1 acre is 1/640th square miles. Then how many acres is this many square miles, right? 640 acres, basically, is 1 square mile. Let's just write it that way. 640 acres is 1 square mile. So if we multiply this by 1.25, 1.25 square miles is 640 times 1.25. There are a lot of ways we can write that out. We can do proportions, things like that. This number I think is supposed to be 800. So 800 acres. Just take my word for that. Hopefully I did that right. So 800 acres is the amount we need. They did ask, they did not ask, but they are using a density per acre. So we're going to have to use acres when it comes to area for this. So there's our area. That's our area. Okay, not the answer. We have our density of 15 people per acre. So now we need that unknown population. So same thing as the previous problem, only with more finessing to get the area itself. So 15 people per acre is how much population out of the 800 acres that we have. We're going to multiply both sides by 800. So 800 times 15. 8 times 15 is 120. So add a couple zeros. That's 12,000 people. That feels like a lot, but that also kind of has to be the answer if I did everything else right with that. So 12,000 people would be the population of Central Park at one given time. That's why I feel like it's so big, because so many people can fit inside it. I wonder if that's some sort of event or if that's very commonplace. Seems like a lot of people, but Central Park's also pretty big. Hey, 15 people per acre. I still don't know what an acre is. I know it's 1/640 square miles or whatever, but I don't know what that looks like conventionally, you know? All right, number 9, problem solving. About 79,000 people live in a circular region with a population density of 513 people per square mile. Find the radius of the region. So this time, we don't really know our area portion of this. We know it's circular. We know we're going to use pi r squared. But this time, we have the population of 79,000. And the density is also known. This is going to be 513 people per square mile. Let's figure out the miles, the square miles. No, the radius in terms of miles. We do kind of find area first, though, right? So density 513 is population over. Now, you could do a couple things. I could say area here and then do the area stuff. But if you already know your area is pi r squared, we can work straight into that as well. Now, there was an example like this. And what I'm going to do, I'm going to follow the means of the example. You multiply both sides by pi r squared. You don't technically need to multiply the pi, because your goal is to solve for r, and maybe next time I won't move the pi with this. But what this will do is bring this out of the denominator so we can start to solve for r itself. So now I have 513 pi r squared equals 79,000, and as you can tell, we need to get r by itself, so I'm going to divide both sides by 513 pi, and you can see this is why I didn't need to necessarily bring pi up, because it came right back down with it. So if r squared equals this amount, r is going to equal the square root of this amount, right? I can take the square root of both sides, and that's what we're dealing with when it comes to r. It's the square root of 79,000 over 513 pi. A lot of, that's exact. It's exact, and it's a lot of, I don't really know what that looks like as a whole. That's where the calculator comes in, and I'm going to let it do its thing. So let's go to the calculator. Let's do square root of 79,000 divided by, use parentheses here, once again, 513 pi, if you're using the same kind of calculator I am. I did not type the pi button. There we go. And that's going to give us our answer of around 7. 7 what? This is a radius? 7 miles. 7 miles. We skipped past area, so I didn't officially ever figure out what the area was. If I wanted to figure that out, I would just do 79,000 divided by 513. They didn't ask for it, though. They did ask for radius, straight up. So I went straight to that. Okay, number 10. About 1.15 million people, population, live in a circular region with a population density of about that number, 18,075 per square kilometer. Find the radius of the region. Same kind of problem. This answer is just in kilometers, though. So population 1,150,000 peeps. I don't even know how many people live in my city or anything, but I don't know how often they talk about circular regions, though, either, right? 18,075 people per, this is square kilometer, per square kilometer, like that. So now we're going to find this radius, same kind of idea. So 18075 equals 1, 2, 3, 4 zeros out of pi r squared. This time, and if you kind of notice what happens and what switches places and not, I'll leave the pi down. I'm going to move this guy up, and I'm going to move this guy down. It's a switching placey thingy, multiply both sides by r squared, divide both sides by 18,075, and we'll end up taking the square root of both sides ultimately. So this will be 18,075 pi. So now we do the square root there, and I'll go straight to the calculator with that. So this is 1150000 divided by 18. I didn't take the square root yet though. Whoops, square root. All right, this one is looking, it's not rounded to like nearest whole number this time. This one's looking more like 4.5. So I'm going to write that. I'm not going to say it's about 4, it's about 5. I'll say it's about 4.5. Now this is kilometers. 4.5 kilometers is going to be the answer I'll put on that one. Trust the process. Trust the process. All right. Number 11. Error analysis. Describe and correct the error in finding the number of people who live in a circular region with a 7.5 mile diameter. I already see the mistake. And a population density of 1,550 people per square mile. Assuming there's only one mistake made, which is generally the case on these kinds of problems for error analysis, they did say 7.5 mile diameter. Now, we haven't spoken of diameter yet together, but diameter is the entire, it's 2 radii. It's double the length of a radius. If pi r squared is your formula for area, they used pi d squared here. They need to take half of this to find it, which they do say correct it, so we're going to have to do this for ourselves. But they use diameter when they should have used radius, basically. I'm going to trust their numbers are correct beyond that, but it's the wrong number. So we're going to have to do this for ourselves. So let's go and correct that error and state exactly that. They are given the diameter and the area of a circle uses radius. So they needed to find radius. All right, so let's correct their mistake. The radius will be half that diameter, 7.5 over 2, which is 3.75. What is this, miles? Miles. Okay, we're going to use 3.75 instead of 7.5 as they use. Let's do the same bits. 1,550 people per square mile is this unknown, I'll put P, unknown population over pi r squared. And we got to use r, just like that. Now, 3.75 squared is 14.0625. No rounding to be had, please, on that. So P over 14.0625 pi, that's our area. We're going to multiply both sides by that, right? So we're going to do 1,500 times 14.0625. And they didn't show that work, pi. They didn't show that work on their bit, but I'm assuming that what they did was correct afterward. They got significantly bigger population, though, because they used diameter instead. So I'm going to go and calculate this one, 14.0625. All right, I'm getting around, and this is going to be a little bit of a roundup, 66267. It says 0.97, so I'm going to kick this 7 up to an 8. 8 people. So a significantly smaller number than they calculated, and for good reason. It should represent about a quarter of what they have. That's just how that will work out. All right, number 12. They ask, how do you see it? The two islands shown below with the given areas have the same population. Which has the greater population density? Explain. They show you numbers of the area overall, and if they have the same population, the smaller area will have greater density. So the orange one, because they don't say what islands they are, or nations or whatever, the orange-filled island has a smaller area. Therefore, all other things being equal, with population being equal, it will, notice I just typed equation naturally, it will have greater density. It is dividing by a smaller value, right? If I say what number's bigger, x over 2 or x over 7, x over 2 is a bigger number. You're dividing by a smaller value. That's all I have to say with that one. Yeah, 486 smaller than 532. There are more people packed inside of a smaller area in general. Or the same amount of people, but when it comes to density. All right, number 13. Modeling with mathematics. We have a soccer field, folks. Rectangular, right? A soccer field of length L and width W has a perimeter of 320 yards. Write an expression that represents the area of the soccer field in terms of L. Use your expression from part A to determine the dimensions of the field that maximize the area. What do you notice? So the maximizing area thing is something we're going to use the calculator with eventually. So let's start with the whole perimeter idea. Perimeter of, let's start with this. Length, width, length, width. That's how this thing works, right? Now, we know area is length times width, but perimeter has to add your two lengths and your two widths, like that. Now, they said, write an expression that represents the area of the soccer field in terms of L. In order to do that, hold on. Area is length times width. Now, there's a W here. We need to re-represent W in terms of L as well, so we can use that with perimeter. Now, we do know that the perimeter is also, 320? 320 yards. So what we can do is get W by itself in this equation. Let's subtract 2L from both sides. And then if we divide everything by 2, then we'll have W by itself in this equation, which will be in terms of L. Then we can substitute that expression for W in the area equation, and we'll have only L represented, expressed. So W is going to equal 320 over 2, which is 160, and 2L over 2 is 1L. So 160 minus L. That's what the width is. 160 minus the length. Okay. So if area is length times width, let's substitute 160 minus L for W, and now we have an area thing expressed in terms of L. And I like to distribute something like this here. This would be 160L minus L squared. That's the best representation to area for me. It kind of shows the quadratic representation that it is. And it's really nice to kind of do this as well because, I mean, you'd have to take calculus to talk about how you maximize without use of a calculator. But if you see this thing as a graph, it says if the length is 0, the area is 0, and it's an upside down parabola. Somewhere here, there's a length for which the area is maximized, and we're going to figure out what that is. You can use other means to figure this out. It's the vertex, but we're going to use the calculator to figure this one out. Yeah, we'll go and use the calculator. I imagine it's 80. I think it's supposed to be 80. So let's go ahead and go to the calculator and figure that out. So for me, the calculator is going to this y equals equation thing. L is our x, like this. X squared, like that. And I'm going to just use this table function thing over here. I'm going to start at 0, and we're going to increase by 1. This will be a little small in terms of working this out, I think. You can see how how the area is growing larger as we go like this. I said it's supposed to be, I think, around 80. So let me go by increments of 10 instead and show you that idea. This is when length is 10, 20, 30, 40, etc. How the area is still getting bigger. And I think at 80 it peaks, right? I think at 80 it peaks. And then when you go farther down, you can see the symmetry and it goes down again. Now, I can start at 80 and go by ones and show you the same thing here, that it still peaks at that value. That right there, 6,400 square feet is the maximum area when the length is at 80 feet. This is feet? Yards, excuse me. Square yards and at yards as well. So that's what we're getting there based off the calculator. All right, based off the table. Like I said, if you know something about finding vertexes and understanding what kind of graph that is, you can figure out as well. But maximum, this was part A. This was part A here. And part B, use your expression to determine the dimensions of the field that maximize the area. What do you notice? So max area is 6,400 square yards. The length of this thing would have to be 80 yards. That's just the nature of what it was. Now, if you want to find the width, you can use 160 minus L. Width is 160 minus 80. which is 80 yards as well. So the dimensions are 80 by 80. Doesn't matter which one we're talking about, right? They're the same. And I think that's what they're saying as far as what do you notice? Length and width are the same. Now, are most soccer fields a square? No. I don't know how wide they are. And I don't know if they're always measured in yards. I think maybe they're 120 yards if I think of a football field that has a soccer goals on it. I don't know. Something close to that. I don't know if they use yards or meters. But length and width are the same. That's the dimensions. So are they generally the same in most soccer fields? No. They're asking how you would maximize area given that perimeter. How you can make the largest area out of it. Is that their goal? No pun intended. Is that their goal when they're trying to make soccer fields? No. It's a math question. And it's a good math question. Okay, number 14. Modeling with mathematics. You are using a 9-inch paint roller to paint a wall of your bedroom. That's this right here. The roller has a diameter of 1 5/8 inches, okay, and a nap thickness of 1/4, I guess it's this thing, 1/4 of an inch, the fuzzy material on the side of the roller. Okay, surface of the roller. How much area does the roller cover in one full revolution? Okay, there's a lot to unpack here. Let me actually just copy and paste that circular image. And we'll go from there. Okay. So, what number? 14. First of all, paint roller, like this guy right here, whenever it starts painting, that 9 inches is a part of what it does, right? When it rolls on a wall, right? Imagine this is the paint roller itself, and rolling up the wall right there. It's going to be covering this width. It's going to be covering this width of 9 inches up the wall as it rolls alongside that. So area we're talking about is rectangular with 9 inches by however much this rolls to complete one revolution. How much does it roll to complete one revolution? Well, one revolution of this is the circumference of that guy right there. And to find circumference, we need to do 2 pi times the radius. That means we need to find the radius of this thing from that inner portion out to the end of the nap, if you will. So radius. So how do we find that radius? The diameter of the inner part is 1 5/8. I need to divide that by 2. And then I need to add the 1/4 inch to that. Okay? So the radius is going to be, this isn't going to look good, but 1 5/8 divided by 2 plus 1/4. Now there are easier ways I can write that, and I'm going to do that right now. 1 5/8 is also 13/8. 13/8. Okay, I'm not going to state why. If you don't know, try and work that out. You could use a calculator, right? You use decimals. I imagine for these, we're going to do a little bit of fraction work for now. They started off that way. Divided by 2 is times 1/2. And we still have that plus 1/4. And times 1/2, we multiply across there. That's 13/16. So that's the radius of just the little guy there. Now, 1/4 is also 4/16. I need a common denominator there. And that's 17/16 inches. A little more than 1 inch of radius. But I'll leave it as a fraction for now. Maybe maybe decimals will be a better served thing later. Anyway, one full revolution is going that entire circumference, and that's going to be that kind of length that we're referring to right here. The length is the circumference for one full revolution, and we'll multiply by that width of 9. So we still need to find the circumference as a whole. Circumference is 2 pi r, 2 pi times radius. 2/16 is 1/8, so that becomes 17 pi over 8 inches as a circumference. The area of one revolution is going to be that length times the height of 9. And I'm doing this exactly for now. I don't know what 17 times 9 is, 153. So 153 pi over 8 square inches. That's an exact value when it comes down to it. I'm going to go and use the calculator right now and figure that out. Oh, I still have that table up. 153 pi divided by 8. It's giving me approximately 60.08. This is one where, because it's not people, I feel like I want to use decimals. Maybe 60 is the right number to say, 60.1. For now, I'll say 60.08 square inches of paint coverage. Just one full revolution is going to give us that amount. So that's kind of what we're doing with that one, right? That's how that's going to work out. Yeah, the circumference is what was all, and I did use the fractions as long as I could. I don't know if that's reasonable or not to do so, but you know what? They stated them as fractions, so I'll use it. And that was part A. That's part A. Part B says the wall is 8 feet high. Painting vertically. Oh, the wall is 8 feet high, period. Painting vertically. You start at the bottom of the wall and make 8 full revolutions with the roller. Are you more than halfway up the wall? Justify your answer. So I can take this number. Remember, I have an exact one in my calculator. Let me pull it up. I have this exact value in my calculator right here. I'm not going to use the rounded value. I'll use the exact one. Let's do, they said 8 revolutions? Let's do 8 revolutions of this. So let's take this and multiply it by 8. Remember, this is in inches, square inches, I should say. Wait a minute. Are you more than halfway up the wall? I don't need the area number. Let's not use that. Let's not use that. Forgive what I stated. Let's use the circumference number instead. So let's go back. So part B, the revolutions, it doesn't matter about the width, right? The 9 inches has nothing to do with how far up the wall you go. It's just about how much coverage you have. So let's go to the circumference value, 17 pi over 8. Circumference is 17 pi over 8. That, for me, is height, right? That's, I'll say height is. So for one full revolution. Now, the height of 8 revolutions is taking that number times 8. Those cancel, you're left with 17 pi inches. That's still in inches. Pi inches. I don't know the exact number, so it's 17 pi, or the approximated. It's 53. I can tell you this answer is going to be yes. So this is around 53.41 inches. That's in inches. In feet, you would divide it by 12. So divided by 12, I'm doing this all on the calculator, by the way. That's around 4.45 feet. 4.45 feet. Now, they asked if after doing this 8 revolutions, if you're more than halfway up the wall. The answer is yes. Now, I technically could have probably answered that earlier because we knew, oh, wait. I don't know how much 17 pi over 8 inches was. But if that's more than a foot, and if you do 8 revolutions, you're trying, well, I should stop talking. Anyway, 4.45 feet is more than half of 8. Half of 8, right? More than 4 feet. So yes, you're more than halfway up the wall. More than halfway up the wall. I justified it mathematically. I don't need to explain more after that when I show all the math on it. Okay, that's probably the best way of going about that. Again, the 9 inches had nothing to do with that portion. Part C. A 3-inch roller. Was this called a 9-inch roller? Yeah. So turn this 9 into a 3. Has the same diameter and nap thickness as the roller above. How much area does the roller cover in one full revolution? How does this compare to the area in part A? So I don't want to make a mistake of assuming it's just a third of it, because that might be wrong. But if now we're talking about, well, it should just be a third of it. Yeah. When we're finding that how much area does it cover in one full revolution, area here is going to be straightforward. The length times the width, or whatever we say, 17 pi over 8, one full revolution. 17 pi over 8. Well, it exactly equals 51 pi over 8 square inches, but let's use the calculator part of that. Now, this is one where I'd almost want to use the exact values instead of the rounded ones. This does round to about 20.03. The other one was 60.08. You can tell that, they are rounded, right? If I did do one divided by the other exactly, though, so comparing, so let's look more at the 51 pi over 8 divided by the 153 pi over 8. you'll see that a lot of things kind of cancel. The pi's and the 8s really cancel, and 51 over 153 is actually 1/3. So it's 1/3 the area covered, and that makes sense because only one dimension changed, and it was only 1/3 of that in that sense. And that should be part C. Okay, that's it for number 14. We only have 6 more problems to go. They seem to get a little longer as we go, though. In exercises 15 and 16, describe how the change affects the surface area of the right prism or right cylinder. You're going to have to know how surface areas work for these things, and I'm not going to get a long explanation for it. I'm just going to give you formulas for the most part. So number 15, doubling all the linear dimensions. So what we originally have here, let's start with our originals. We have this guy where, I guess I have to get a little bit of an explanation. The surface area of a prism is same as a cylinder. It's the lateral area plus the area of your 2 bases. Now, I consider my bases to be, say, on top and bottom. It's not always the case, but I consider these to be on top and bottom. The area of the bases, let's start with that. Area of each base is going to be 17 times 4, which is 68. 68 square inches. The lateral area is the area of these 4 facings here. Front, right, back, and left. Now, the lateral area... Oh, sorry, that's 1 base, by the way. 2 bases is going to be 2 times 68, 136 square inches. Now, the lateral area is going to be the perimeter of your base times height. So I'm not going to get deep in that formula, but perimeter of your base, you add 17, 4, 17, and 4. Okay, so perimeter is 2 17s plus 2 4s. 34 plus 8 is 42 inches. Your height is 5 inches. That's where that's going to be used. So your lateral area is 42 times 5. 42 times 5 is 210. We get 210 square inches from that. So your overall surface area of this guy, that's an S, sorry, S, surface area, is lateral area plus area of your 2 bases, and that'll be 346 square inches. Now that's just the original one. We're going to be doing it again with a different calculation on this whole set. Okay, so that is that's it on number 15. So let's go ahead and double everything now. So as we double everything, now we're talking about turning these things into 17 goes into 34, 4 turns into 8, and 5 turns into 10. So these are our new that we're talking about right there. So kind of just, utilize all those. Maybe I should write them here. 34, 8, and 10. Now, I don't know if they're expecting you to know how these things change. I did mention it before. If we're doubling everything should now be 4 times bigger in terms of area. You're squaring the 2. But I'm working surface area with you either way. So let's do it all again. Surface area is lateral area. Let's try that kind of fast. Perimeter of base, 2 34s plus 2 8s, times height. Height is 10. Plus area of 2 bases, 2 times 34 times 8. So a lot more to kind of unpack there once we get all this calculated. Listen, I'll just go straight to the calculator this time. Let's see if this actually works out. It should. But let's do it all in one fell swoop. So in parentheses, I got a 2, and then 34 plus 2 times 8, double close parentheses, times 10. This is why it's good to write things exactly as you want to calculate them. Plus 2 times 34 times 8. And le voilà, 1384. So 1384 square inches. So how does that compare to the original, right? If you double them, so compare, let's do 1384 divided by 346. And when I do that, I'm getting 4. That's what I expected. 4 times bigger. We're talking about surface area. Surface area is 4 times greater. So that's what we're doing on that, right? We compute surface area of one, surface area of the other, divide that. Now, if we triple the radius, this is just the radius, not everything, just the radius. This is not going to be 9 times bigger or just 3 times bigger. This I actually want to compute this one. So tripling the radius, let's consider the original cylinder, surface area of a cylinder. It's also lateral area plus area of your two bases. However, in this case, your base areas are pi r squared. So pi times 2 squared, which is 4 pi. Let's leave that for now. 4 pi square yards. So 2 bases is going to be 8 pi square yards. Now, your lateral area, it is also perimeter of base times height, but this perimeter, in this case, now your base are these guys right here, right? Perimeter here is circumference. So circumference, 2 pi r times height. 2 pi r. So 2 pi times your radius, 2, and the height of the cylinder is 7. Doesn't matter that it's going across like that. It's the distance between your bases. So that'll be 28 pi square yards of lateral area. So we're going to add together, and I'll leave this in terms of pi. I'm not going to round it. Let's do lateral area of 28 pi plus 8 pi of your area of your two bases. And that's 36 pi square yards in total. That is the original. If we triple the radius, now we turn the radius into 6. Let's change color as well, in fact. Radius is 6. And we do have to calculate everything new because the base area is going to change, lateral area is going to change. So base area now are new. Base area now is pi times 6 squared, which is 36 pi. So 2 bases is 72 pi. Much bigger. It's already bigger by surface area just from the base areas alone. The base areas of these alone, one base area was equal to the surface area of the whole thing. So tripling radius clearly has an effect. Lateral area is perimeter of base, circumference, 2 pi r times your height of still 7. 12 times 7 is 84. So it's 84 pi square yards. So your surface area this time is 36 pi. Your two bases, 72 pi. Hold on, let's do that again. Lateral area is 84 pi plus 72 pi, which is going to be 156 pi square yards. How does the new one compare to the old one? What is 156 pi over 36 pi? Let's figure it out. Can you see what I write here? I think so. Let's try this. Compare 156 pi over 36 pi is about, and I don't know, 4.3 repeating. Let's get the fraction version of that. Let's kind of make it an improper fraction. Let's reduce it. So 13 thirds. So 13 thirds times larger. 4.3 repeating. Okay. So it's not some exact version. Like I said, it wasn't 9, it wasn't 3. 13 thirds times larger when you do that comparison, one versus the other. So a little different. And I think that time I really did have to work that out. 13 thirds is also 4 1/3, right? 4.3 repeating. Okay, let's move forward. We got 4 more questions to do. Like I said, these are kind of taking a while. Number 17, modeling with mathematics. A playground ball with a 16-inch diameter has a rubber coating on its surface. Does a ball with a diameter that is 1/4 times the diameter of the given ball need 1/4 times the amount of rubber coating? Explain. What's the radius of the ball uses half of the amount of rubber coating? Okay, so a few things. Playground ball, that's a sphere. Okay, so a sphere. I can't draw spheres very well, but there it is. 16-inch diameter. We're talking about this being 16 inches. Obviously, we're going to want to dive into radius. So 16 over 2 is 8. Let's see what they want. What do you want? Does a ball with a diameter that is 1/4 times the diameter need 1/4? Okay, rubber coating. So rubber coating is the surface. Now let's first talk about surface area of a sphere in general. Surface area of a sphere is 4 pi r squared. Either something you need to know. I know this was one of the very last sections, if not the very last section of your IM2 textbook, like 11.6 or something, whatever it was. So this is used there. So if you took IM2 and you took the thing, well, here we go. So 4 pi r squared, we're going to have 4 pi times 8 squared, 256 pi square inches of the original sphere. Now, if you have a new radius that is 1/4 that diameter, it's also going to be 1/4 of the radius. So 1/4 of 8 is 2 inches. Now that surface area is 4 pi times 2 squared, which is going to be 16 pi square inches. They're asking if you need 1/4 the amount of rubber coating. No, you need, so compare, I don't really know how to say this. I should say ratio. I should put K equals or something like that. But 16 pi over 256 pi, this is 1/16. You need 1/16 amount of rubber coating. Once again, and I'm kind of uncertain whether they expect you to know how areas compared to each other. You should based off of IM2 stuff, but now that they're talking surface area, they want to confirm you square your scale factor. If the scale factor is 1/4, 1/4 squared is 1/16. That's what we need for that. We got to practice some formula stuff with it. That would be part A. Part A, 1/16 the amount, not 1/4. Part B, what's the radius of a ball that uses 1/2 the amount of rubber coating used to cover the 16-inch ball? So this one's a little bit different. This time we have the surface area, if you will, because surface area should be half of 256. So part B, half of 256 pi is going to be 128 pi square inches. That's your surface area, and we need to find the radius for that. So 128 pi is 4 pi r squared. We need to find r in this scenario. So I'm going to begin by dividing both sides by 4 pi, like that. Boom, 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 cancellation. 128 over 4, I believe, is 32. So r squared is 32. R is the square root of 32, which is 4 root 2. Root 16 times root 2 is 4 root 2 inches. I don't feel like rounding that one if they're talking about having exactly that amount that'll be exactly half. I will give you a rounded value. 4 times root 2, or square root of 32, is 5.656, so around between 5 and 6, around 5.5 inches of radius, but that's going to be more of the exact value that you have there. All right, number 18, 3 more questions. A cylindrical swimming pool has a diameter of 24 feet and a height of 4 feet. Let's draw that. So we got a cylinder, folks, we got a cylinder, and there's our swimming pool. So diameter going across is 24 feet, and the height is 4 feet. A smaller pool with the same height has a diameter of 12 feet. Okay, so that's not quite half. Let's try that again. Maybe something like that. Same height. Not drawn to scale, by the way, y'all. So diameter of 12 feet. And this is also still 4 feet. They said same height. A vinyl liner covers the bottom and side of each pool. Okay, we'll see where that comes into play. Well, here's the thing. The top sounds like it's uncovered. So if we talk about surface area, there's going to be something there. Does a smaller pool require 1/2 the amount of vinyl liner that's used to cover the larger pool? Explain. If not, estimate the diameter of the cylindrical swimming pool that uses half the amount of vinyl liner. Assume the height of the pool is 4 feet. So this one's interesting as far as if we just talked surface area only, I'd say the answer is no. Or no, excuse me, I'd say the answer is yes. Because only diameter is being halved, not the height. Actually, I don't know if that's true. Actually, that wouldn't be true. But the top is uncovered. They said the vinyl liner covers the bottom and side. Top is uncovered. So when it comes to surface area, and I need to compute this, I feel like, not just want to. Surface area of the pools are going to be, for each of them, normally we'd say lateral area plus the area of both bases. In this case, we're only referring to the area of the bottom base here, not the top. That doesn't have any vinyl covering on it. So doesn't matter which one we're talking about, but we'll call this object 1 and object 2. I probably should have done that for the others. So the surface area of object 1, pool 1, the bigger one, lateral area is, actually let's start with base area, pi r squared. Radius here is 12, radius here is 6. So this will be pi times 12 squared on that part. Lateral area is the circumference times the height. So that is 2 pi times that radius of 12 times the height of 4. So our surface area in terms of pi, we have 12 times 4 is 96, 96. 96 pi plus 144 pi, which is 240 pi square feet. That's the surface area of the first one in terms of vinylage. Surface area of the second one, we're going to be doing 2 pi, its radius was 6, that height is still 4, and then pi times the radius 6 squared. Let's see how this one compares. So 6 times 4 is 24, times 2 is 48, so 48 pi plus 36 pi, which is 84 pi square feet. So when it comes to comparison here, it says, does a smaller pool require half the amount of vinyl liner used to cover? No. No, it does not. How much? I'll say K instead of compare this time. Surface area 2 over surface area 1. This is how I should have been writing them before anyway. So 84 pi over 240 pi. It's almost a third, a little more than a third. So 84 over 240, that can clearly reduce. But let's see what kind of decimal they give us. 0.35. So 0.35 times smaller? I don't know. I'll say 0.35. You need 35% the amount. So you need 35% the amount of vinyl for the smaller pool. Yeah. I don't know if I could have known that to begin with when it came to explanation. Even if it was fully covered, I'd say that it would need probably still not 1/2, but now that the top isn't covered, that's kind of how I'm going to refer to that one. So, yeah, there you go. Anyway, there is the first guy. Was there more to that question? Estimate the diameter of the... Oh, we still have to answer that part. Estimate the diameter of the cylindrical swimming pool that uses half the amount of vinyl. So we need to basically solve for R in that scenario. Now, look, we found the 240. We're going to use that. I'm going to go to the next page, though. So this is 18A, continued. Continued. All right. So here we have half of 240 pi, which is 120 pi square feet. So that surface area, 120 pi, is going to be 2 pi. They said assume the height's still 4 feet. 2 pi r times height plus 1 pi r squared. We have to solve for r in this scenario. It's a quadratic. Okay, interesting. Now I could, and I will, I'm going to divide everything by pi in a moment here. But 2 pi, let's see. 2 times 4 is 8, so we have 8 pi r plus pi r squared. Here's the thing, y'all. Everything has pi in it. If we divide everything by pi, we can wipe it out. So 120 equals 8. Whoopsie. 8r plus r squared. This is a total quadratic equation. I'm going to subtract 120 over here. I'm going to write this way. Excuse me. Let's see if this is factorable. 24 and 5, 12 and 10. I don't know if it's factorable. I'm going to assume it's not factorable for a second. Let's actually go back. Let's do completing the square. R squared plus 8r plus blank equals 120 plus blank. So ignore that one. 120 plus blank. Divide this by 2 square. Yeah, this is not factorable. So this is completing the square, something you would have done in IM2. You can also use quadratic formula. So 136. Take the square root of both sides. R plus 4 is square root of 136, plus or minus square root of 136. And R is negative 4 plus or minus square root of 136. Now I'll tell you right now that the minus 1 will not apply, so I'll just use that one. So negative 4 plus square root of 136. That is 7.66. R is around 7.66 feet. Now they need a diameter, so we got to double that. Now here's the thing. I have an exact answer here that I want to double. Times 2, and I'm getting about 15.32. D is about 15.32 feet. That's not exact, it's approximated, but there was so much in the way of the square root that I think we're going to have to kind of leave it like that. So it does turn into a quadratic equation, one that was not factorable. Completing the square or quadratic formula will be used to solve. So use what you need for that. I'm sure you can go to a table, right? I could, if I used my calculator, I could have also done this because now we've used table things to approximate, right? I could have set this guy equal to 0 or subtracted 120 over and did x squared plus 8r plus 8x minus 120. And you can try numbers until it works, basically. So I could have done, and figured out where I hit 0 on this thing. Now I hit somewhere, this is radius, by the way, right? So I would have hit somewhere between 7 and 8, and then you kind of keep working off that. So, start at 7. So this is something you would do in this scenario. It's kind of a guess and check of sorts, somewhere between 7, 6. You notice it was 7.66. So if I go to 7.66 here, which remember it's rounded, and I go by 0.001, like that. You'll notice here, that's where that change goes from here to here. Again, I rounded, and then I doubled that value afterwards. So yeah, there are a lot of ways you can do it, but again, if you're an IM3, you probably dealt with quadratics previously. So that's what I did here in finding it. That was part A. Let's do part B. That was all part A. Part B says, to install the vinyl liner, it costs $195 per square foot. You have $1,000 in your budget to spend on the liner installation. What is the largest pool you can get without going over your liner budget? Assume the height of the pool is 4 feet. So what I'm going to do here is I'm going to divide 1,000 by 1.95 to find out how much square footage I can use, and then I'm going to find out the radius with that. It says what's the largest pool. I assume they asked for diameter. So $1,000 divided by 195 per square foot. Let's start with that. 1,000 divided by 1.95. Okay, so this, it has a weird number here. So 512.8205,128. Now that is how many dollars per, that's how much square footage I can have. Square footage. It says what's the largest pool you can get without going over. Can this work as a fraction? Because I'd rather have this exact number, but okay. This is a fraction as well, but I want to try and keep this exact number as much as I can without rounding. So a fraction version I can write in this simplified without any decimals is this. I'll just write it like that, okay? So that's the surface area. That's the largest surface area we can use. So let's do the same things we did before. So 20,000 over 39. And listen, I could use this. I just don't want to round early. And I let my calculator work this one out. You can also use this, of course. It's still exact. But this is the square footage we need. So this is going to equal, again, a lateral area plus area of base. So 2 pi r times this height plus 1 pi r squared, just one base. Same thing as before, only this doesn't have pi in it. So this time I think I'm going to use the calculator a little more, is the word frugally? I'm going to be a little more frugal with my calculator usage. So 8 pi r plus pi r squared. So let's do this. Let's rewrite this and set it equal to 0. Pi r squared plus 8 pi r minus 20,000 over 39 equals 0. This is our quadratic we're going to be working off of. And I'm going to go ahead and use the calculator for this one. I don't think I want to deal with quadratic formula, completing the square here. Should I? Let's try quadratic formula. All right, A is pi, B is 8 pi, and C is this number right there. So check this out. This is how weird it's going to look. R equals negative B plus or minus the square root of B squared minus 4A C, that needs to be negative, all divided by 2a, 2 pi. Now I could do this right now. I could use the calculator right now. I think I will, just because this is so rambunctious. So I'm going to start typing this stuff in. So I'm going to get negative 8 pi. Now, the whole plus or minus aspect, listen, I'm only going to use the plus. There won't be a minus version here that would give me a positive number. So I'm just going to do plus, not plus or minus. The square root of, and I need to do 8 pi squared, which I know that should be 64 pi, but that's okay. I'm just going to type it in exactly as this looks. And you'll see what this looks like afterward. You're going to go, whoa. Minus 4 times pi times negative 20,000 divided by 39. Close that parenthesis, close that parenthesis for square root, and that one for that one, divided by 2 pi. I have to use parentheses for that as well. Okay, this is going to look like this. I hope I did this right. So it's going to look like that mess right there. Notice I only used plus here. I didn't use plus or minus. So negative 8 pi plus, and this is in parentheses here to do the numerator. Okay, let's see if that worked. I don't know if it'll work, but okay, I mean, that should be a radius, and that kind of makes sense as an answer because we saw a radius of like 7 before and 16 and things like that. So, or 12. So I'll trust that answer. That's our radius, 9.387, I mean, 88. I don't know, eventually we're going to round somewhere. That's inches, and if I double that for diameter, that times 2, there we go. So I feel like I'm getting more by using quadratic formula than I would have just by using the table to do some guess and check. So diameter is about 18 point, I'll say 78, not inches. This is feet. What am I doing? Feet and feet. Okay. So feet and feet. We already know it's a 4-foot high pool. So we're just using that part to talk about that. Okay. That is 18. It's just there's more. These problems get longer as we go further. All right, number 19. Making an argument. You ask your friend which U.S. states have the greatest population densities. Your friend says it must be California and Texas because they have the greatest populations. Is your friend correct? Explain. I'm sure they're decent. Actually, they might not be. They have maybe the greatest populations. But densities, they also have among the largest areas. I think Alaska's the largest. So Alaska is very sparse in population itself, so its density is also going to be sparse, but that's why they're not using Alaska as an example. Your friend, my friend isn't necessarily correct because California, well, just because areas, but California and Texas have very large areas as well, and population considers area. All told. I'm guessing this is me not knowing anything of the actual answer, and I'm going to Google it in just a second. I'm guessing New York, Florida, Pennsylvania. I'm guessing those ones have greater densities than population densities in California and Texas. I'm going to Google it right now. I don't know if I can have you see this on the screen. Let me find out if I can do this. Give me a second. Google. Will this work? New tab. Okay, I think this will. All right, so check this out with me here. Transition, does that work? All right, can you see that? I think you can, right? Nope, you can't see anything. Sorry, let me try that again. Can you see that? Nope, it shows up and then it goes away. I don't know why. Okay, it goes away the moment that I try. Okay, maybe you can't see it then. Okay, never mind. Sorry, that won't work. All right, but I'll go and Google it. Largest population densities by state. All right. Oh, Hawaii. Okay, let's see. Okay, I ran into an article. New Jersey. Forgot about New Jersey. Highest density. Okay, none of these articles are showing me exactly how I want to see it. It looks like it's, I don't know what I saw with Hawaii. That didn't seem to work right. Looks like New Jersey's number 1. Rhode Island. Okay, I guess they just have a lot of people. It's a very small area. Massachusetts, Connecticut. Wow, I was way off. Maryland, Delaware, then Florida, then New York, then Pennsylvania. Those were actually next. I don't know where California is there, but those were like the top 9 or so. Okay, I was pretty wrong, but that's number 19. That's number 19. So yeah, friend is wrong, right? Texas is pretty sparse. I mean, it's very massive. It has a lot of people, I guess, but Actually, I don't know if Texas has a lot of people. It has a lot of, metropolitan areas, Houston, Dallas, things like that. But it's big. It's big. Same with California. All right. I'm trying to find my windows again. Here we go. Last question, number 20. Thought-provoking. Give an example from your everyday life of an object whose surface area changes. Sketch the object and determine what geometric shape can model it. Estimate the dimensions of the object before and after the change, and explain how the surface area is affected. That's a lot. My first thought went to like balloon, but a completely deflated balloon's no longer like a sphere. Even an original balloon, you can argue, is not really a sphere, but we can say for argument's sake that it's spherical instead of like an ellipsoid. So if I said a balloon, let's say a less inflated versus a more inflated, right? We can have a sphere. So here's, bigger and smaller. Okay, it has some sort of radius in comparison. R1 and R2. I don't really know what we're going to say here. Estimate the dimensions of the object before and after the change, how the surface area is affected. Here, the whole radius, if we're actually talking sphere, the entire thing's affected in that way. So surface area of object 1 is 4 pi times R1 squared, and surface area of object 2 is 4 pi times R2 squared. Let's say it was half of the radius. Your your surface area is 4 times smaller. If radius is halved, then surface area is 1/4 of original. I don't know if that's the best example. I got to think of some other ones. Well, I don't know how this one would work. It's probably not perfect. Well, I was first thinking soap bar. Soap bar can kind of be a prism, rectangular prism. I know it's very curved, but then I was thinking of ice cube. The reason I was thinking of that is because I'm literally thinking of the word cube. So how about ice cube? And let's say it's a cube. I don't know if it's exactly a cube, but the real question is it still a cube when it melts? So here's the original ice cube. Okay, but when it melts, does everything become smaller version of it as it kind of melts around it, right? That's what I'm thinking there. If these lengths are length, width, height, and this is length, width, height right there. I don't really know how to answer this question that's being asked. Oh, you know what? You know which one could work well is like a candle, because it's cylindrical in nature, but then it just melts its height. The thickness doesn't really change, and it's a cylinder. So how about a candle? So a candle is a cylinder by nature, at least the kind of candle I'm thinking of. So I have a candle here, which has some height. Okay, here's the, it's like that. And then later, it melts, but the cylinder shape is still the same. So here's height 1 and height 2, but the radius doesn't change. Radius, radius. So this one just becomes whatever proportion that is. So K is H2 over H1 in that case, and surface area is still H2 over H1. Actually, that's not true, because the base area doesn't change. The bases don't change, so I guess surface area isn't perfect in that way. But yeah, you have the height, and then you have slightly different the lateral area is half, but the base area doesn't change. I don't really know how to answer that one perfectly with that stuff in mind, but those are just some examples of things. Balloon, if you deflate it or inflate it. An ice cube, if it melts. Candle, if it melts. I was thinking soap bar as you dissipate it more, but I don't know which part dissipates more. It's not exactly one of the shapes we're talking about. Let me think of some other things that can change. I'm thinking like you open a cereal box, whatever, but it's still the same surface area. So I don't know. I think I'll just leave it at those ones. Just that's the idea. It's very open-ended, thought-provoking. So I hope that those kind of cover it. All right, guys. And now that we're hitting our hour and a half mark, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. This is the beginning of our IM3 journey together in section 1.1. We're going to move on to 1.2 next with the lecture and stuff. But you can download things down below. Excuse me, PDFs down below, and check out the timestamps for things you want to find more of. So that'll do it for this one. This is Mr. Robinson. Thank you so much for watching, and I will see you in the next one. Take care.